Okay, so in this video, we will find the area of a general ellipse. So take two real numbers, a and b, to be positive. And if you recall, the ellipse is a generalization of the circle. So it looks like an egg, more or less. Given by the equation x squared over a squared plus y squared over b squared is equal to 1. Now if you let a and b to be equal to r, you can multiply across by r squared and you get the familiar x squared plus y squared equals r squared, the equation of a circle. But as a and b are positive, they may not necessarily be the same, and this will essentially skew the shape of the circle into what's called an ellipse. Let's find the intercepts. So if we look at the x-intercepts where y is equal to 0, we get this term equaling 1. There are two obvious solutions. X is either positive 8 or negative 8. And the same goes for the y-intercepts. If we set x to be 0, then this term is equal to 1. And so either y is b or negative b. And again, if both a and b are equal to, say, r, where r is some positive number, then all of the intercepts are either r or negative r, and we recover the circle of radius r. But here we have, again, an ellipse, the generalized version of a circle. Well, let's isolate y in terms of x to find what curve or curves are making up this ellipse. So if we isolate first this term, let's put a common denominator, so everything under a squared. And then if we multiply by b squared, we obtain that y squared is b squared times this. We'll combine the b squared over the a squared together, times a squared minus x squared. And finally, we undo the square by taking the square root. There are two obvious solutions. Y is either the positive or the negative of the root of all this. Well, we can simplify here, since a and b are positive. The root of this term is simply b over 8 times the square root of this term. And so the ellipse is made up of two functions. The positive square root, of course, times b over a, gives us the upper half of the ellipse, and the negative square root gives us the lower half of the ellipse. Now here we can take advantage of the symmetry and finding the area of this one piece of the ellipse, if you want the first quarter, and then clearly by symmetry the area of this piece is equal to that of the other three pieces. So if we find the area of this region, then quadruple it, we will obtain the area of the entire ellipse. So let's redraw the picture, but focus on the first quadrant. Well, since we have here a portion of the ellipse in the upper half of the semicircle, y is positive, so we take the positive solution. So here y is equal to the positive of this term. So y is simply b over 8 times the root of a squared minus x squared. And now we can find the area of this region. So again, let a, uppercase A, be the area of the entire ellipse. And let's call the area of this region A1. we know how to find the area of a region, right? We find the area first of an infinitesimal rectangle, and then we will sum the area of the rectangles here from 0 to 8, and this will be done, of course, by integration. So the position here is at x. The width of our rectangle is an infinitesimal change along the x-axis. So the width is, of course, given by dx. All we're missing is the height of the rectangle, which is, of course, the corresponding y value given this value of x on the curve, and y is given by this. So the area of an infinitesimal rectangle is given by the height, which is this term times dx. So we have b over 8 times the square root. This is the height of our rectangle, times, of course, dx being the width. And now we have the area of an infinitesimal vertical slice of the region. To obtain the total area of this region, A1, we have to sum the area of all of these infinitesimal rectangles. So we have to integrate from where to where? From 0 to 8. The span of the region along the x-axis. X starts at 0, goes all the way up to 8. And this integral will give us the area of the entire region of the quarter piece of the ellipse. And as we've just said before, to find the total area, we will, of course, simply multiply this by 4. So 8 is simply 4 times of A1. So once we find A1 times 4, and we have the area of the ellipse in its most general form, where A and B are arbitrary positive real numbers. So now we're down to just a straightforward integration. Well, first thing is, well, we can obviously factor b over a, as it's a constant multiple. And we're left with a rather interesting integral, mainly because of the square root. And this is not a trivial integral, but if you look, we have a constant minus x squared. We can use here a trigonometric substitution to eliminate the square root. So let's do that. I'll put the details over here. So we will let x be close to sine of theta, but this won't quite work because this will give us a squared minus sine squared. What we want is, of course, 1 minus sine squared, and so to factor a squared out, we need here out of x squared a multiple of a squared, so we multiply sine by 8. So once we square x, we get a squared sine squared. And so a squared minus this becomes a squared minus a squared sine squared theta. We can factor a squared, and we have 1 minus sine squared. And of course, 1 minus sine squared is cos squared. So we can take the square root of this term, and we will be left with a cos theta. So already we've eliminated the square root, but we have to, of course, find the differential dx and the new bounds of integration. So if we take the differential here on both sides, then dx is the differential of this function, which is, of course, a cosine of theta d theta. So now we have dx. All we're missing are the new bounds of integration. So let's see. This is x is equal to 0. Well, x is a sine theta, right? So if x is 0, we have 0 equals a sine theta. Since a is a positive constant, sine of theta must be 0. and of course sine of 0 when the angle theta is 0. We now need the other new bound of integration when x is equal to a. Well, if x is a, this becomes a equals a sine theta. Again, since a is a positive constant, we can divide across, and this becomes 1 equals sine of theta. And of course, sine of theta is equal to 1 when the angle theta is pi over 2. And now we can complete the trigonometric substitution. So the integral in terms of x will now become an integral in terms of theta. Again, b over a is a constant multiple. It stays there. When x was 0, theta is 0. But when x is a, theta is pi over 2. The square root term is simply a cos theta. And the differential, dx, if you recall, is a cos theta d theta. We can factor out a squared, as again a is a constant multiple, so we'll have a squared over a, which will cancel to a, so we have ab, the integral from 0 to pi over 2. And cos times cos is, of course, cos squared. Now, how do we integrate cos squared? If you recall, since we have a single even power of cosine, we have to use the half angle formula. And if you recall, for cosine squared, it is 1 plus cos of 2 theta over 2. The half here is a constant multiple. We can factor it out. And we're left with integrating 1 plus cos of 2 theta. This is now a rather simple integral. So if you integrate 1 with respect to theta, it is of course simply theta. And the integral of cos of 2 theta is sine of 2 theta. But be careful, if you think of the chain rule, the derivative of this will give you cos of 2 theta, check, but then times the derivative of the inside times 2. There is no multiple of 2 here, so we have to divide by 2. We now have the antiderivative, and we must, by the fundamental theorem of calculus, evaluate the antiderivative from 0 to pi over 2. And now we just have to sub in and evaluate. ab over 2 is a constant multiple. Let's leave this out. Times the antiderivative at pi over 2. So this will give us pi over 2. Plus, well, replacing here theta by pi over 2, well, twice of this is pi, so plus sine of pi over 2, minus, at 0, well, here we obviously get 0, plus sine of 0 over 2, and this simplifies quite nicely because, of course, sine of 0 is 0, and sine of pi is also 0. So both of these terms vanish, and we are left with pi over 2 times ab over 2. So we're left with, if we put the pi first, pi times a times b over 4. A remarkably simple answer, but remember, this expression is only the area of a quarter of the ellipse, and so to get the total area of the ellipse, we have to multiply the answer we just found by 4. So finally, the total area of the ellipse is 4 times this value. The 4 over 4 cancels, and we have a remarkably simple answer, simply pi times AB. And this is the area of a general ellipse. And it is consistent with the special case of a circle of radius r. As we've just said, if a and b, not as we've just said, but as we said in the beginning, if a and b are equal to r, then this is r squared, multiply across, you have the equation of a circle of radius r, the area of which is pi r squared. And if a and b are equal to r, this becomes r squared, and we recover the area of the familiar circle, pi r squared. So just a beautiful application of integration and a trigonometric substitution. So again, the area of an ellipse in general is simply pi times AB, and that's it.